let's continue with limit cycles. Okay. You remember that there were centers in linear systems, right? They were spirals that were going in and spirals that were going out. Okay? However, we didn't have something that, in all cases, there's just one point at the origin where the system approaches to or revolves around, etc. There's no such case as, like, there is a trajectory, let me just, like a trajectory, and the system approaches that trajectory and stays at that trajectory. Not necessarily a circle, maybe something weird, like this. So to have this, you have to be nonlinear. I hope I'm making sense. Am I? Yes? Because if you are linear, you can't have this. All right. A limit cycle is an isolated closed trajectory. Isolated means that neighboring trajectories are not closed. They spiral either towards or away from the limit cycle. So, for example, this is a stable limit cycle, this is an unstable limit cycle, and this is a rare occasion of half-stable limit cycle. It goes in, but from outside. So it's repelling inside, it's attracting on the outside. It can't be repelling on the inside, right? Okay. Look, this one is approaching and approaching. This one is repelling and repelling. This one is repelling and approaching. Do you see it now? If all neighboring trajectories approach the limit cycle, we say the limit cycle is stable. Limit cycles are very important scientifically. They model systems that exhibit self-sustained oscillations. In other words, these systems oscillate even in the absence of external periodic forcing. Of the countless examples that could be given, we mention only a few. The beating of heart, the periodic firing of pacemaker neuron, daily rhythms in human body temperature, hormone secretion, chemical reactions that oscillate spontaneously, dangerous self-excited vibrations in bridges and airplane wings. In each case, there is a standard oscillation of some preferred periods, waveform, and amplitude. If the system is perturbed slightly, it always returns to the standard cycle. So it's very lifelike behavior, okay? Consider this one, for example, a simple limit cycle. This equation is given in cylindrical coordinates, right? R dot is r times 1 minus r squared, and theta dot is 1. Do you understand this system? Yes. So it keeps rotating. If you are inside the rotating thing, you go out. If you are outside, you are pulled in. Typical oscillator. Okay? Very nice. Then there is van der Pol oscillator, a less transparent example. So what do we have here? We have our typical harmonic oscillator, right? Because typical damped harmonic oscillator would look like this. Right? X dot. But here, B is a function, and this one would be linear, right? This one, in its current case, is a linear system. But making it like this, x squared minus 1, we make it not unlinear, nonlinear. You left at unlinear, okay. Okay. So, what is going on here? It's basically saying that it has a nonlinear damping term which is like this. This term acts like ordinary positive damping for x greater than 1. So if it's greater than 1, if x is greater than 1, it damps the oscillation. But if it's less than 1, it has a negative damping, meaning that it increases the oscillation. So that in the end, you always approach to x equals to 1 amplitude oscillation. Make sense? Doesn't make sense? Doesn't make sense. Okay. Let me see. So normal damped oscillation would go like this, right? But imagine that once you hit below 1, there is a negative damping. So it basically takes this system out to here. Now imagine this negative damping is everywhere, so it would go like this, right? Wouldn't fit into a page. So then you have a normal damping that brings it back. So whenever it goes out, it's damping. Whenever it goes in, it's undamping it. Okay. One can prove that the van der Pol equation has a unique stable limit cycle for each mu greater than 0. Okay, we happen to have a van der Pol oscillator somewhere here. Let's see. Not responding. Do you see the van der Pol oscillator? Mu times x squared minus 1 times x dot, etc. So for this one, mu is 1. Let's see what's going on if we are running this. We have to close this one first. Okay. So I don't know why I have this line. We don't need that line, right? Let me get rid of that line. Where is it? Can you find it? You see, wherever I start, whether I start here, 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 it goes to the same cycle. Are you happy with this phase portrait?
How?
Yes?
How?
What do you mean, how?
How do we show that this happens?
Okay, we will do it rigorously, but not for this one. We will do this Poincaré-Bendixson theorem. Do you know it?
Oh.
No?
I think I read New Dynamical Systems book.
We will come to this, but we will not do it for this system. Okay, we didn't do, for example, starting from inside. So let me do the outside again. So if I start from here, it's here, but if I start from inside, it's also going outside. Do you see? No matter where you start, the system attracts itself to that attractor. What if mu is really small? Then it's still a limit cycle, but it's being approached much slowly. So, yes? Then, very good. Mu is really big, then it's quite distorted and it's like this. But no matter whether mu is really big, like once it's greater than 0, you have a limit cycle. But what if mu is negative?
I expect it to go up.
Then you have an unstable limit cycle. You see, if you are outside, it flies off to infinity. If you are inside, it falls down to 0. Why? Because if you have mu as negative, then once it's less than 1, it damps, so it goes to 0. Once it's outside 1, it undamps, it flies to infinity. We are happy?
Yeah.
Good. Very good. We can continue this discussion. Poincare-Bendixson theorem. Okay? Now that we know how to rule out closed orbits, which is we skipped, we turn to the opposite task, finding out to establish that closed orbits exist in particular system. Here's the theorem. You should have a closed bounded subset of the plane. Fx should be continuously differentiable vector field. R does not contain any fixed points. And there exists a trajectory C that is confined in R in the sense that it starts in R and stays in R for all future times. Then either C is a closed orbit or it spirals towards a closed orbit as t goes to infinity. In either case, R contains a closed orbit. Okay, the proof is subtle and requires some advanced ideas, so we don't go into it. But the keyword is topology. And for us mortals, it's something like da. It stays inside. Of course, it should approach something, right? That's the way I approach mathematical proofs when they are in 2D, right? So maybe I'm being cynical. I'm not trying to be cynical. Just the point is that, let me remind you something. These trajectories cannot merge, right? So we are talking about trajectory that stays inside, right? So, and there is no fixed point. So it has to approach a closed orbit, a limit cycle. It has to approach. It gets closer and closer, but just doesn't cross itself. It just gets infinitely closer and closer to that orbit. So, when applying Poincare-Bendixson theorem, it's easy to satisfy conditions 1 and 3. What were they? Closed bounded subset of the plane, continuously differentiable, does not contain any fixed points. Okay, these are easy to satisfy. What is hard is to make sure that the trajectory will be confined in R and will never go out. Okay, that's the hard part. How can we be sure that a confined trajectory exists? The standard trick is to construct a trapping region. Okay, a closed connected set such that the vector field points inwards everywhere on the boundary of R. So we need to find a boundary and to show that on top of this boundary all the vectors are pointing in. If we can show that, then we can say that the trajectory will remain inside because there is no way out. Are you following?
Yeah.
Still following? Yes. This is your homework, by the way. Then all trajectories are confined. If we can also arrange that there are no fixed points, then Poincare-Bendixson theorem ensures that R contains a closed orbit. Okay, for example, this one is a nice example. Okay, this is our main example that we will do, and it has biology, so some of you may find it interesting. In the fundamental biochemical process called glycolysis, living cells obtain energy by breaking down sugar. In intact yeast cells, as well as in yeast or muscle extract, glycolysis can proceed in oscillatory fashion. with a concentration of various intermediates waxing and waning with a period of several minutes. So, a simple model of these oscillations has been proposed by Selkov in 1968. Did you notice how many Russians there are in this business? Very good. In dimensionless form, the equations are like this. Is it a nonlinear equation?
Yes.
Yes, we have x squared y, x squared y. Okay? Where x and y are concentration of adenosine diphosphate and F6P, fructose 6-phosphate. Phosphate, I don't know which one is right. A and B are greater than 0. Construct a trapping region for this system. That's what we need to do. So let's just draw the system and see what's going on here. What is this? What do you think it is? Its formula is this, b over a plus x squared. If you compare with this, that corresponds to y dot equals to 0. Right? When y dot is equal to 0, b minus ay minus x squared y equals to 0, y equals to b over a plus x squared. Are you with me? Yes? So that point corresponds to the places where y dot is 0. That's why on top of it, everything is horizontal. Just like before, we decide on which direction these arrows take by looking at x dot. And we did it once, we don't need to do it again, right? On top of this line, which is x dot equals to 0, it goes up and down. As you can see, we already see a ghost of a limit cycle here, right? Now we need to get a limit cycle, we need to first find a trapping region. The book did it for us. Here is our trapping region, okay? So let's do it. Let's just write this equation again. I think I can do this. Let me see. No, I can't do that. But, okay. Let me just copy down these equations and I will use them. X dot equals to minus x plus ay plus x squared y, and y dot equals b minus ay minus x squared y. I'll copy this, maybe cut this and paste it here. So, consider this line. What do we need for it to be a trapping boundary?
All derivatives points inside.
Yes, which derivatives? X derivatives, right? Yeah. If x derivatives are positive, then we are going in, right? Let's see what happens in that boundary. It's x equals to 0. So at x equals to 0, x dot is, for x equals to 0, x dot is ay plus x squared y. X is 0, so it's just ay. So if y is greater than 0, and since we know that a is greater than 0, x dot is greater than 0. So we have that boundary now. This boundary is done. Are you still with me? Yes? Yeah. Let's do this boundary. That's y dot equals to 0. No, y is equal to 0. And we are looking at y dot, right? What is y dot? Y dot is b. Is b positive? B positive, so that's also a trapping, that's also a good wall that shows everything goes in. How about this one? So that's x equals to b over a. Is that right? X equals to b over a. Y equals to b over a. Y equals to b over a, and we are looking at y dot. Right? What is y dot? B minus a times b. Yeah. It's minus x squared y. So this cancel out. What is minus x squared y?
Something negative.
Something negative. Do you agree? Because y is positive and x squared is positive, so minus x squared y is negative. Are you still with me?
How did we choose y is equal to b over a? Mathematically speaking, if I was to do this question, how do I guess, okay, b over a is what I choose?
You know, we don't accept just anyone to this program of MSN, right? Or to Bilkent University. In smart people with trust. Let's see if you will be able to figure it out in homework. But you will figure it out, no worries. If you don't, you can ask the previous people. I asked the same question, so. But once it's given to you, you understand it, right?
I understand the logic, but how are we, okay, y-axis, x-axis was okay, but how are we saying, okay,
Yeah. B over a is just, you want y dot to be negative at some point, right? At some point. So you say, okay, why don't I make this one 0? Because this one is going to be negative anyways. That's how you find it. You see? And then there is this part, which is tricky, I guess. What is that part? In any case, there is also this part, which is the most tricky part. In particular, consider this one. Okay. You understand it. It's a trapping region, right? You can read it if you want. But the point is that we are not done even if we have a trapping region. We also shouldn't have a fixed point. But we do have a fixed point. Do you see that fixed point? Over here? Yes? How do we get rid of it? Well, by surgery. If this fixed point is unstable, right, then we can just close on top of it and just surgically remove it. So our Poincare-Bendixson theorem tells us that we have everything in place, like all the things, 1, 2, 3, 4 things in place, only if this one is unstable. That way, we know that every trajectory enters from here and remains there, but also if this is shrunk really, really small towards the unstable fixed point, then everything is coming out of that unstable fixed point, right? So we should have a limit cycle there. When do we have a limit cycle? When that point is unstable, right? How can we decide if that point is unstable or not? We can use what we have learned today, right? We can linearize around that point. So that's what we are doing here. This is the Jacobian at that point. We magically calculated it. And after doing some algebra, we realized, so what do we want for it to be unstable? Let me see. Delta is definitely greater than 0. So we are somewhere here. For it to be unstable, we also need to be here, right? Which means that tau needs to be positive for it to be unstable. So tau equals to 0 occurs when b squared is equal to this. And you can draw this. This is b, this is a, stable fixed point, stable limit cycle. Because here it becomes an unstable fixed point, and that leads to limit cycle. You see how nice it is? So this whole thing, first of all, those people, modeled real system with equations, and then they also realized what parameters are needed for it to be in the limit cycle regime. So that's how it looks like, and I have, so let's also take this one. Sorry, I have to fix this. So, for example, if I have b equals to 1 and a equals to 0.08, let's see what will happen. What is Poincare 8? Okay, now I remember. Okay, b is equal to 1, a is equal to 0.08. Okay, what do you expect? We expect to get a stable fixed point and no limit cycle. So let's run it. Do you see these lines are there, and it seems like there is something there, but no, it's a stable fixed point. So it falls down inside. Okay? Now let's do it for 0.6, 0.06. Okay, 0.06, 0.6. Seems like nothing changed, but you now have a limit cycle, right? Do you see the limit cycle? No matter where I start, I end up at the limit cycle. Are we happy? So in Poincare 8, I am changing the orbit smoothly. Okay, let's see what we have. We are at b equals to 0.6, and I am going in a sinusoidal way between, for some reason I chose this, why not 0.13, right? 13. Okay, it was multiplying this. Okay, sorry. So I'm going between 0.05 and 0.13. 0.05 is somewhere here, 0.013 is somewhere here. So I'm going back and forth here. What will happen? The stable limit cycle will shrink down to a point, then it will shrink back out, etc. Right? Okay, let's see. Okay, this is not what you are supposed to see, so let me stop it. Just stop it. I think this is the reason. Okay. Stable limit cycle, shrinking to a point, setting out like a point, then shrinking out again to a limit cycle. So I'm changing parameter again, going into the stable fixed point, then coming back, and unstable fixed point leads to limit cycle. Good? Bless you. Okay. MATLAB is unresponsive just on the right time. We are done with it anyways. So this thing of having a stable fixed point and then turning into a limit cycle while this one becomes unstable is called Hopf bifurcation. It's yet another type of bifurcation. Okay? All right. So Poincaré-Bendixson theorem is one of the central results of the nonlinear dynamics. It says that the dynamical possibilities in the phase plane are very limited. If a trajectory is confined to a closed bounded region that contains no fixed points, then the trajectory must eventually approach the closed point. Nothing more complicated is possible. This result depends crucially on the two-dimensionality of the plane. In higher dimensional systems, n greater or equal to 3, the Poincaré-Bendixson theorem no longer applies, and something radically new can happen. Trajectories may wander around forever in a bounded region without settling down to a fixed point or a closed orbit. In some cases, the trajectories are attracted to a complex geometric object called a strange attractor, a fractal set on which the motion is aperiodic and sensitive to tiny changes in the initial conditions. Okay? Sounds familiar?
Yeah.
From before? Yes. This sensitivity makes the motion unpredictable in the long run. We are now face to face with chaos. We'll discuss this fascinating topic soon enough, but for now, you should appreciate that the Poincaré-Bendixson theorem implies that chaos can never occur in the phase plane, in the 2D phase plane. Okay, phase plane means 2D already. Okay. Any questions? No questions. Any comments? As you can see, we are skipping a chapter here. We are skipping from 7 to 9. Since I have 10 minutes, maybe I can discuss chapter 8. Yes? Maybe. Let's just go to the book. Just going through it really quickly. So we have bifurcations revisited. I'm in particular yet another Russian. Oscillating chemical reactions. For an application of Hopf bifurcation, we now consider a class of experimental systems known as chemical oscillators. Have you heard of this?
Yeah. There's a tune one at the cover page of Nile Reds.
Cover page of what?
Nile Reds. Some chemistry channel.
Okay, yes. These systems are remarkable both for their spectacular behavior and for the story behind it. After presenting this background information, we analyze a simple model for oscillations in the chlorine dioxide iodine malonic acid reaction. The definitive reference on chemical oscillations are here. Belousov's supposedly discovered discovery. So in the 1950s, Russian biochemist Belousov was trying to create a test tube caricature of Krebs cycle, a metabolic process that occurs in living cells, when he mixed citric acid and bromate ions in a solution of sulfuric acid and in the presence of cerium catalyst, whatever. He observed to his astonishment that the mixture became yellow, then faded to colorless after about a minute, then returned to yellow a minute later, then became colorless again and continued to oscillate dozens of times. Today, it comes as no surprise that chemical reactions can oscillate spontaneously. Such reactions have become a standard demonstration in chemistry classes. But in Belousov's day, this discovery was so radical that he couldn't get his work published. He was it was thought that all solutions of chemical reagents must go monotonically to equilibrium because of the laws of thermodynamics. Does it make sense to you now as well? I mean, I would also expect that. But Belousov's paper was rejected from one journal after another, and one editor even added a snide remark about Belousov's supposedly discovered discovery. Belousov finally managed to publish brief abstract in obscure proceedings in Russian medical meeting, although his colleagues weren't aware of it until years later. Typical Russian story, right? Nevertheless, word of his amazing reaction circulated among Moscow chemists in the 1950s, and 1961 a graduate student named Jabotinsky was assigned by his advisor to look into it, and Jabotinsky confirmed that Belousov was right. And his work to light at an international conference in Prague, a few times where Western and Soviet scientists were allowed to meet. At that time, there was a great deal of interest in biochemical oscillations, and the Belousov-Jabotinsky reaction, as came to be called, has been a manageable model of those more complex systems. Okay. So what is this reaction? The reaction looks like this. And it has a similar two-dimensional thing going on, okay, which leads to a limit cycle. It gets much more interesting because this is just chemical reactions happening in one place, and it goes and they start oscillating. But what if you also include the diffusion, right? They are chemical reagents and they can diffuse. Right? When you include diffusion,
right-hand sides, right?
Hmm?
And applying to the right-hand sides then.
Exactly. Like, yeah, I can't write on top of it, but that leads to very interesting stuff, like
reaction diffusion equations.
Let me show you. Something like this starts happening. So it's not only oscillating in one place, but that oscillation is traversed throughout the space because it's also diffusing.
Actually, there's an interesting story behind reaction diffusion equations as well.
You mean the Turing mechanism?
Yeah, Turing found them, and interestingly, it was an explanation for the stripes of zebras.
Exactly. This is a nice simulation, but for example, this one, although this is yet another version of it. So it starts like an oscillation and then it turns into these patterns of spirals, etc. Okay. So chapter 8 is not an uninteresting thing. It's just I didn't want to get carried away with it. What else do I want to tell you? For example, I forgot to mention the connection between Mandelbrot set and Feige and logistic map. Did I mention that? No? Do you know the connection? No. Okay. Let me just. Do you know the connection?
Between Mandelbrot and logistic map?
Yes.
Incompletely.
Okay. Let me complete your knowledge. Here it is. So, okay, let me show you. If you do these nonlinear transformations, basically the z equals to z squared plus c equation for Mandelbrot becomes x equals to lambda times x times 1 minus x equation. They become the same thing. And in fact, on the real line, it becomes exactly the same thing. And you might remember the period 3 window in logistic map, right? And you might remember the period 3 medallion, the copy of Mandelbrot set there. So they are the same thing, okay? That's the connection. And if you look at it from the sides, they are the same thing, okay? Okay, very good. I think we can stop here. Thank you very much. Take good care.